Section 4.6 is rational functions and models. A rational function is a function that may look like a fraction where p of x and q of x are polynomials and q of x cannot be equal to 0. Q of x can be equal to the constant function 1, which means that if you have p of x equals x squared plus 2x plus 1, that would still be considered a rational function even though it doesn't look like a fraction, because you can take anything and put it over 1 and turn it into a fraction. So this would still be considered a rational function. I just don't want you to get tripped up on your homework. The domain of a polynomial function is all real numbers, but the domain of a rational function is going to be all real numbers except what makes the denominator equal to 0. In example 1, we're asked to determine if the function is rational and state the domain. Is this a rational function? Do I have a polynomial on top and a polynomial on bottom? Yes, it is a polynomial on top and a polynomial on bottom, so this is rational. The domain is going to be all real numbers except what makes the denominator 0. Is anything going to make this denominator 0? I have x squared plus 1. Is there a number that I can square and get a negative 1 so that this zeroes out? Not a real number. There is a complex number, but when I'm asking about the domain, I'm talking about the real numbers. So the domain here would be all real numbers from negative infinity to infinity. Is this a rational function? This is not a rational function because remember, you have to have integer powers of x. You can't have a square root. But what would be the domain of this function? Can I take the square root of 0? Yeah, I can, but I can't have a 0 in the denominator of a fraction, so I don't have 0 in the domain. And also, I can only take the square root of positive numbers, so that means that this domain would go from 0 to infinity. Now, on this one, I need to go ahead and factor the denominator. When we factor this denominator, it factors into x minus 1 times x minus 2. Is this a rational function? Yes, it is. What is the domain of this rational function? Okay, you want to give me my answer in interval notation. So it goes negative infinity to 1. It might be easier if we write what x cannot be. X cannot be equal to 1 and x cannot be equal to 2. So this interval, if I wrote my domain in interval notation, I would say it's the interval from negative infinity to 1, union 1 to 2, union 2 to infinity. On a pencil and paper test, you can write your answer like this, but on your homework, my math lab will probably want you to write your answer in interval notation. Where this denominator is equal to 0 is where the graph of the rational function has what's called vertical asymptotes. The line x equals k is a vertical asymptote of the graph of our function if the y values approach infinity or negative infinity as x approaches k from either the left or right. If you look at the graph of this rational function, the denominator is equal to 0 at x equals 2. Well, at x equals 2, our y's are going off to infinity as we approach 2 from the right, and they're going off to negative infinity as we approach 2 from the left. A vertical asymptote is just a vertical line that the graph will not cross. Your graph will never cross a vertical asymptote. This notation means as x approaches 2 from the right. The superscript of plus means that we're approaching 2 from the right. So as we approach 2 from the right, the y's are going off to positive infinity. As x approaches 2 from the left, we go down to negative infinity. This is a vertical asymptote, and vertical asymptotes occur where the denominator equals 0. If I ask you to find a vertical asymptote, all you do is you set the denominator equal to 0 and solve for x. Horizontal asymptotes are a little trickier. The line y equals b is a horizontal asymptote of the graph of f if y approaches b as x goes to either positive or negative infinity. So this horizontal line right here is considered a horizontal asymptote because as x goes off to infinity, the graph approaches this line but never equals it. As we go off to negative infinity, the graph approaches this line at 1 but it never equals it. Now, unlike the vertical asymptotes where your function will never cross it, it is possible for your function to cross a horizontal asymptote close to 0. The horizontal asymptotes are determined by what happens out at positive and negative infinity. How we find our asymptotes? Well, our vertical asymptotes are easy. We just set the denominator equal to 0. but you've got to make sure that your function here is in reduced form. If you have a factor that makes both the numerator and the denominator equal to 0, you don't have a vertical asymptote, you have a hole. So our caution right here is if you have a factor that cancels between the numerator and the denominator, that's where you have a hole. Whenever you're finding your vertical asymptotes, you want to factor and reduce your rational function first, because any factor that will cancel between the numerator and the denominator is the location of a hole in your graph. And we'll see an example of that in a minute. The hole would be located wherever x is equal to 0 for that factor. To get your horizontal asymptotes, you end up comparing the degree of the numerator with the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then the x-axis is your horizontal asymptote. So if you have a proper fraction where the degree on top is smaller than the degree on bottom, then the x-axis is a horizontal asymptote. If the degree of the numerator equals the degree of the denominator, then your horizontal asymptote is going to be a line where you have y equals leading coefficient over leading coefficient, and we'll see an example of that in just a minute. If the degree of the numerator is greater than the degree of the denominator, then you have no horizontal asymptotes. In example 2, we're asked to use the graph to determine any vertical or horizontal asymptotes. Here's the function that generates this graph. If I were to factor that denominator, it would be equal to 0 at 2 and negative 2. That's where I have my vertical asymptotes. So I have vertical asymptotes at x equals plus or minus 2. My horizontal asymptote, because the degree of the numerator is equal to the degree of the denominator, I have a horizontal asymptote at y equals leading coefficient. Here the leading coefficient is 1 over leading coefficient. Here the leading coefficient is negative 1. 1 divided by negative 1 is negative 1. Does that make more sense now what I said, how to find the horizontal asymptote? It's leading coefficient over leading coefficient if the degrees are the same between the numerator and the denominator. On part B, is my denominator ever going to be equal to 0? It's never equal to 0 in the real numbers, so that means that I have no vertical asymptotes. What about a horizontal asymptote? The degree of the numerator is less than the degree of the denominator. That means that the x-axis will be a horizontal asymptote. So I would say that I have a horizontal asymptote at y equals 0, because y equals 0 is the equation of the horizontal line that's represented by the x-axis. Notice also that my graph crosses the horizontal asymptote here at 0. I said that that's okay. A graph will never cross a vertical asymptote, but it can cross a horizontal asymptote. The horizontal asymptote is determined by what happens out at infinity and negative infinity. If I were to extend the domain of this graph, we would see that this graph approaches the x-axis and just gets closer and closer and closer, but out at infinity it never crosses back to the negative side. Over here, as I go to negative infinity, this graph will get closer and closer to the x-axis, but it never crosses back over to the positive side. It only crosses the horizontal asymptote here at 0. Example 3, now we don't have a graph. I just give you the functions and I ask you to determine if there's any horizontal or vertical asymptotes. Before you do this, you always want to factor your denominators so you can see if there's any factors that cancel. Will this denominator factor? I can pull a 3 out and that leaves me x plus 1. I don't have any factor that'll cancel on top, so I do have a vertical asymptote here. Where is my vertical asymptote going to be? At x equals what? Negative 1. It's where the denominator is equal to 0. This denominator equals 0 when x is equal to negative 1. Now to find your horizontal asymptote, the degree of the numerator is equal to the degree of the denominator. So I look at leading coefficient over leading coefficient, and that's going to be y equals 6 over 3. But 6 over 3 reduces to 2. So y equals 2 will be my horizontal asymptote. Notice also, each time I write these asymptotes, I'm writing the equation of either a horizontal or a vertical line, because your asymptote is the equation of a line. A vertical line is x equals a constant, a horizontal line is y equals a constant. On B, will this denominator factor? What's it factor into? X plus 2, x minus 2. Neither one of those will cancel with the factor on top, so where will my vertical asymptotes be? positive and negative 2. Do I have a horizontal asymptote? The degrees are different, but this is a proper fraction because the degree of the numerator is less than the degree of the denominator. The x-axis is our horizontal asymptote if we have a proper fraction for our degrees. The degree on top is less than the degree on bottom. So I have a horizontal asymptote at y equals 0. That's the x-axis. Will this numerator factor? The numerator factors into x plus 1 times x minus 1 over x plus 1. Those factors are going to cancel out, and that means that h of x, the graph of h of x, will look like this. Y equals x minus 1, provided that x is not equal to negative 1. Because after I reduce this I end up with something that's not a fraction, there's no vertical asymptote. The degree of the numerator is greater than the degree of the denominator, so there's no horizontal asymptotes either. If I were to graph this function h of x, I would have a hole in my graph when x is equal to negative 1 and y is equal to negative 2. I would have a hole right here at negative 1, negative 2. And this is a linear function that looks like this. But it has a hole at this point when x is equal to negative 1 and y is equal to negative 2. Where I got the negative 2 from was I plugged in the negative 1 into my reduced fraction and solved for y. So negative 1 minus 1 is negative 2. So I graphed the linear function x minus 1 because that's my reduced fraction, and I just put a hole in that graph of that line y equals x minus 1 at the point x equals negative 1. Anytime you have a factor that cancels between the numerator and the denominator, that's where you have a hole in your graph. And your graph would be the reduced function. I don't go over this again, but it is an important concept. I don't do another example in the notes. You will see this again, I promise, in pre-cal. Don't know that you'll see it a whole lot in college algebra, but it is in pre-cal and calculus and everything else. This is an important concept. If you don't have a horizontal asymptote, you may have a slant or an oblique asymptote. Oblique is just another way of saying slant. A third type of asymptote, which is neither vertical nor horizontal, occurs when the degree of the numerator is 1 more than the degree of the denominator. So here, the degree of the numerator is 1 more than the degree of the denominator. If I were to use long division and divide this polynomial, it would reduce to this, where the remainder would be 3, and x minus 1 goes into x squared plus 2 evenly, x plus 1 times. The equation of your slant asymptote is going to be the equation of your quotient when you divide without the remainder. Your slant asymptote is going to be a linear equation after you divide and you ignore the remainder. The only time you would have a slant asymptote is if the degree of the numerator is 1 more than the degree of the denominator. How you get the equation of that slant asymptote is you use division. So I could divide this using synthetic division. What number would I put over here for the synthetic division? I have 1x squared plus 0x plus 2. What number goes over here? 1. So I would divide. I'd drop down the 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 2 plus 1 is 3. This number is the remainder, and that gives me 1x plus 1 for my quotient without the remainder, and I would say that that's equal to y, and that's where this slant asymptote came from. It's what you get when you divide without the remainder. What part of it's confusing? What I was doing was I was simplifying this function. I was just doing the synthetic division on this function. So my numerator is what I'm dividing into, and so that's 1x squared plus 0x plus 2. 1x squared plus 0x plus 2, and I'm dividing that by x minus 1, so I put the 1 out here. Remember, you use the opposite sign here from the factor. And then I did the synthetic division, and what I'm left with is this right here is equal to 1x plus 1, which is this, plus 3 over that factor, x minus 1 that I divided by. It's the remainder over the divisor. So the part that you get after the synthetic division that is not the remainder, that is your equation for your slant asymptote. It's a linear function. And we did have a vertical asymptote at 1 because that's where the denominator was equal to 0. A slant asymptote, because I graphed the equation of this line with a dotted line, and my function would approach that line but never cross it. Now we can graph rational functions using transformations if we understand what the graph of the parent function looks like. The most basic rational function we have is y equals 1 over x. So what I could do is I could make a t-chart to get some points to plot. So if I pick different values for x, plug them into the function and solve for y, and that gives me sets of ordered pairs. So I have a point at -2, -1/2, that's this point right here, -1, -1, that's this point right here, -1/2, -2, that's this point right here. When x is equal to 0, this is undefined, so that's where my vertical asymptote is. That's why I don't have a y value here. If x is equal to 1/2, 1 divided by 1/2 is 2, so that gives me this point. And then I get these other 2 points, connect the dots, and I have a horizontal asymptote at the x-axis, y equals 0, because the degree of the numerator is less than the degree of the denominator. That's why I have a horizontal asymptote here. I have a vertical asymptote at x equals 0, because that's where the denominator is equal to 0 here. This is your parent function that you can then graph other functions from using transformations if your rational function is in this form. Looking at the transformations, and I think that was in section 3.5 video if you need to go back and review graphing using transformations. Looking at this looks like the parent function where I have a vertical shift up or down. Down how many? And do I shift it to the left or to the right? Left how many? Remember, vertical shifts are outside the function. They move with the sign, so that's why this is down 1. Horizontal shifts are inside the parent function, inside that 1 over x, and they move opposite the sign. So this is not going to go to the right 2, it's going to go to the left 2. Then all I do is I take this graph up here and I shift it down 1 and to the left 2. I'll do this by hand. So my vertical asymptote gets shifted to the left 2. Remember, originally the vertical asymptote was the y-axis. Well, now that moves to the left 2. My horizontal asymptote gets moved down 1. So there's my asymptotes, and then I just sketch in the graph using some points. And there's the shape of the function. And that's how you would graph this using transformations. And that wraps up section 4.6.